Hello and welcome everyone. Very happy that we're all together again. In this tutorial, we will continue performing the power stability analysis on the ETAP software. So let's start. First of all, and before performing the stability analysis, we need to run the load flow analysis to check that all things are okay and the power flow is going well from and to the different components of the system we have. So let's run the load flow analysis. Here, load flow. Then we press on this run load flow tab and okay. And here we can adjust the different units. Here, display option. Set the power flow units in megavolt ampere and okay. Very good. You can see the first load, for example, is absorbing a power value of 90 megawatt plus 60 megavar, and the first generator is injecting a power of 150 megawatt plus 46.9 megavar. And by the same way, we have one marginal alert here for this busbar where the voltage drop across its terminals is less than 5%. Also, the voltage level across this first busbar is 100%, and the voltage level across this second busbar after the transformer is 100.4%, and the voltage level across this busbar here connected to this generator is 103%, as we have set the voltage level or the designing voltage level of this generator to be 103%. So all things are okay now. After that, we can run the stability analysis if we press on this tab here, Transient Stability. And as we have learned it before, there is a difference between the steady state stability, the dynamic stability, and the transient stability. As we said before, the transient stability analysis is used to evaluate the ability of the system to maintain synchronism when subjected to large disturbances such as a short circuit or sudden load change or loss of generation or loss of transmission lines, for example. So we will analyze the system stability now for a fault case like a short circuit case. And as you see, the left column here has been converted to the different tools that we can use for the stability analysis. So we can use those different tools to perform the transient stability analysis. And before analyzing the system results, we need to adjust the study case by pressing on this tab here, Edit Study Case, and we can go directly to the Events tab and drag this tab to the right a little bit. As here in the Events tab, we need to add an event for the fault that will happen in the power network to see how the generators or how the system can respond to this fault, or to see if the system is able to maintain its stability after clearing this fault. So we can set the total simulation time, for example, to be 35 seconds. And we can add an event, and it will occur at second number 5, and we can set its ID to be fault, for example, fault number 1, and press on OK. And at this event, we can add an action related to the first transmission line, which is this one here. So a short circuit condition will occur at this transmission line. Hence, we add an action and we set the device type to be a transmission line. Here a line. Then for the device ID, we set it to be line 1, as this is line number 1 that we are focusing on. And for the action, it will be a fault, as we will have a fault on this transmission line. And for this percentage, it asks us for the percentage of the total length of the transmission line that the fault will occur at which. For example, we can set it to be 30% here, which means that the fault will occur at a distance of 30% of the total length of this transmission line starting from its left point here, which means that if the total length of this transmission line is 900 meters, for example, the fault at this case will occur at 300 meters from the starting point of this transmission line from its left point here. And we press on OK. After that, we can add another event for clearing this fault. So we press on Add. Then we can set its name, for example, to be clear fault number 1. And we can set its time to be at second 5.1, which means that this fault will last for 0.1 second or 100 milliseconds. So we have a fault on the transmission line that takes 100 milliseconds. This is because we will clear this fault on another action related to this event, which is to open those two circuit breakers. So we press on OK and we add an action related to this second event. Here it's related to the circuit breaker, and circuit breaker number 1, we will open it. We will set its action is to open the first circuit breaker and press on OK. Also, we add another action related to the second circuit breaker to open it. So add here circuit breaker number 2 this time, and its action is to open it and OK. So when opening those two circuit breakers, the fault will be cleared. So a fault will occur at the transmission lines at second number 5, and the fault will be cleared at second number 5.1 when those two circuit breakers are opening. Also, we can open the next tab, which is the plot tab. And here we need to select the different devices that we need to plot the transients topology data for. So we need to plot the data for generator number 1 and generator number 2. Here select generator number 1 and generator number 2. And by the same way, we need to plot the passes or the different passes we have. Busbar number 1, 2, 3, 4. You can see the busbar that we press on is marked with this X sign, which means that we have selected it in the plotting operation. Also for the lamped loads we need to plot the different lamped loads. Lamped load 1, 2, 3. And now we press on OK. And here we are ready to run the transients topology analysis. If we press on this tab, run transients topology, and set its name, for example, to be transients topology, and OK. Here it's loading. The calculations are done. Very good. Now we can drag this tab, transients topology time slider, to the right a little bit, and we can adjust the units from the display option tab. Here set the power flow units in megavolt ampere and OK. Very good. As you see, at the normal case, the system components are running according to its different ratings with no problem. For example, the first generator injects a rated power of 150 megavolt ampere with a voltage level on its terminals of 100%. And for the power angle of this generator, it's 20.5 degrees. So this is the stable power angle that the system is producing the rated power of 150 megawatt. And by the same way, for the EFD, or the excitation field voltage, which is the DC voltage applied to the rotor windings to produce the rotor magnetic field, it has a value of 1.5 per unit. And also, this generator is having a rated speed of its rotor of 1500 revolutions per minute. So for the first generator, it works with its rated parameters of the voltage, the power, the excitation field voltage, and its speed with the ideal values. And the same idea for the second generator, as it injects a rated power of 122 megawatt and it has a power angle of 0. This is because we have set this generator to be at the swing mode, which means that it's the reference that the rest of the system is measured with respect to, and also its excitation field voltage is 1.6 per unit, and its speed by the same way is 1500 revolution per minute. Also, the voltage across its terminals is 103%. So at the normal operating case, all things are okay. And we can check that if we drag on the transient stability time slider. Here, when we go right on this slider, you can see all of the generators and the different loads parameters are constant with their different parameters when we go on the time, but before the second number 5. So before reaching second number 5, all things are okay as the different parameters remains constant. But here, suppose we go at second number 5. Here, if we start exceeding the second number 5, as you see, the power angle changes. As the power angle increases a little bit, you can see its value now is 20.66, then 20.82, then 21.04, and also the voltage across the different busbars is decreasing from 100% to P 68% for the first busbar and 56% for the second busbar, and also 82% for the third busbar we have, and so on. And this is a logical thing because when the fault occurs, the current increases very high and the voltage decreases highly. But suppose now we have exceeded the fault time. Here, when we exceed the time of 5.1 second, when we exceed it to P5.14 for example, you can see the two circuit breakers open now, so the fault has been cleared. But we need to know how the different generators can interact after this fault case or after this transient case. Will the generators be able to remain the rated speed with the rated power angle and the rated voltage levels or not? And this will appear when we go with the time domain. Here, when we go, you can see the power angle for the first generator is increasing 22.6, 22.9, 23.3, 24.4, 24.8, and so on. So instead of the rated value of the power angle of 18 degree at the stability case, the power angle now is increasing. Also, the voltage level across the first generator terminals is increasing gradually, and this is as an attempt of the power system to restore its stability and recover its rated values for its different parameters. Here, the power angle is increasing to avoid changing the generator speed to maintain the frequency of the generated constant at 50 Hz, and also to maintain the synchronization of the generator. As you see, the power angle is increasing by the time, and the output electrical power is directly proportional to the power angle as we learned before, so the output electrical power of the generator is increasing as you see by the time. So the power angle is increasing, and by the same way the output power is increasing to maintain finally the synchronization of the generator by maintaining its rated speed at 1500 revolution per minute, and this is to maintain the rated frequency of the generator at 50 Hz to maintain the synchronization of the generator with the rest of the system we have. More than great. So that's about this tutorial. Hope that's clear right now. Thank you for watching and see you next tutorials.